All right. I will begin. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students. I just pray that you guide our work today and help us to understand what we do, Lord. In your name I pray. Amen. All right, so I think I'm going to start with the latter half of a proof I didn't finish last time to get us started in here. It's Theorem 6. I think it was Theorem 6 I only proved half of. Pretty sure it's this one. So Theorem 6 is the following. Let A be an ideal of a ring R. Then A is maximal. All right. If and only if the factor ring R by A is a simple ring. All right. So proof. I believe we did this way last time. So I'm going to do the converse direction this time. If R by A is simple, then what? Let A be a subset of B, be a subset of R. All right. With B not equal to A. Kind of awkward here, where B is an ideal. All right, so it's an ideal. B is an ideal. We're thinking B is an ideal of R, which somehow fits between A and R. All right. If A is maximal, if we want to show A is maximal, right? So what do we need to show? That B is equal to R, right? All right, so then B mod A is an ideal of R quotient by A by theorem 4. Now, I didn't have time to prove theorem 4 in class, but it would be a good exercise for you guys to work through that. It's relatively simple. But if you're confused about theorem 4, the best way you can get unconfused is actually work through it for yourself, right? And that's something you should be doing. You know, your senior students in a sort of last math course that makes the major what it is. If I were you, I would be working through the sections in the book for yourself, right? I mean, I show you proofs in here, but you got to take ownership of them too, right? So I don't really know any other way to do that except to work through it for yourself. Something you probably should be doing. And some of you are. Let's see here. Now, what else do we know? B over A is not equal to 0. How do we know that?
B's not equal to A.
Right, because B is not equal to A. So B not being equal to A means there's at least something in B which is not in A, and that gives you a coset besides just A in there. Therefore, B over A has to be equal to R over A. Why?
R over A is simple.
Yeah. And then that implies what? That implies that B is equal to R, which implies that A is maximal. All right. Now, so a corollary to that, which bears repeating, is that if R is a commutative ring, I think I said these things, but I didn't write them down last time. Commutative ring, an ideal. And my handwriting is getting me. If R is a commutative ring and an ideal, this is the if, I'm going to restate this so that I can fix the grammar here. Let R be a commutative ring, okay? All right. Then an ideal of R is maximal, right? If and only if what? I actually need to, I'm missing a kind of very important thing to communicate this idea, which is a letter, right? Let's call the ideal M, as in a maximal ideal, all right? Then R mod M is what? Yeah, a simple ring would be, that's true. But we have from our previous work last lecture that that's if and only if what? A field, right? Right. Which is what the last one is what I'm really after here. So it's basically combining theorem 3 with the fact that a field is an integral domain. Okay, anyway, corollary 2. It's corollary 1, I suppose. Corollary 2 states the following. Every maximal ideal of a commutative ring is a prime ideal. Why would that be? I think the sentence I just read is actually the proof of this, not the latter one. Sorry about that. This one is combining results that we had last time. Last time we proved that the quotient by a maximal, we proved that if it's a simple, oh, curses, I was trying not to get back into all that. Yeah, so theorem 5 gave us that if R is commutative, then R is simple if and only if R is a field, right? Which is like the next to last thing I proved last class. It's just, thing fades for me after I get away from it. Okay, anyway, so every maximal ideal of a commutative ring is a prime ideal. How would we prove that? The proof, given the things we have to work with here, is that if it's a maximal ideal, right, then we have a commutative ring, right? So R mod M is what? It's field, right? By corollary 1, which implies what? R mod M is an integral domain, right? A field is a very nice kind of integral domain, right? And then we had a theorem last time that if the quotient of R by M is an integral domain, then M is what? A prime ideal. So I told you last time, these are the two sort of major theorems to remember, is that a commutative ring mod a maximal ideal is a field. Commutative ring mod a prime ideal is an integral domain. And those are if and only ifs. This is the other thing, is that maximal implies prime. However, the converse is not true. Prime ideals are not necessarily, prime ideal does not imply it's a maximal ideal. So it goes, you know, again, maximal implies prime, but prime does not imply maximal. And that actually, to show you that, I need to talk about something briefly that we haven't done yet. And this is one of the things that got left out last time, but I should mention to you that the zero ideal is prime. All right? So I'll be more specific. 0 is a prime ideal in Z, right? Now, can you check that that's a prime ideal? How would you do it? Suppose A, B is in 0, right? Does that imply that A is in 0? Or B is in 0? I mean, the zero ideal only has 0 in it. So, yeah. I mean, but, well, it's, okay, yeah, fair enough. Very good. But the point is, this is a more general comment, that 0 is a prime ideal of any ring, okay? And, well, I guess 0 is a prime ideal of what kind of ring? Integral domain, I should say, yeah. So notice that Z mod 0, right? This is isomorphic to what? Z again, right? So we have Z mod a prime ideal is Z again, but is Z a field? It is not. Therefore, 0 is not a maximal ideal. Of course, I think you could prove that 0 is not a maximal ideal through more direct methods as well, right? I mean, not a maximal. So I'm using what? I'm using corollary 1, which says that there's an equivalence between quotients being fields and ideals being maximal. But you could take a step back and just prove that 0 is not maximal by direct, you know, find an ideal between 0 and Z, which isn't 0. It's not hard to do. How about like even numbers? Okay. All right, so that's that. I just wanted to complete this circle of ideas before we go on, because it's kind of an important things for this course here. Now, I'm actually going to complete the treatment of section 3.3. I thought I was going to go on, but I thought some more about it, and I really think that we should make time to cover the rest of section 3.3 because it's quite beautiful and it deserves our time. Let's see here. So let's see here. And I think we need this. So the rest of section 3.3 can be quickly summarized as the following. If you look at a matrix ring, right? So let R be a ring. Then we know that the n by n matrices, right, which I will sometimes call this Rn by n, you know. So this forms a ring, right? With respect to what? Can't do with respect to. With respect to the usual what? Right, usual matrix addition and multiplication. Very good. So it's worth noting that we can also write MNR as essentially the span. It's the span over the ring of the matrix units, EIJ, if you will. Now here, these EIJs, these are the matrices which have a 1 in the ijth spot and 0 elsewhere. okay, the so-called matrix units. Although that's an unfortunate term because they're not units in the sense of ring theory. They're not invertible elements of the matrix ring. Nevertheless, you can use these to build any matrix. You know, if I have B is an element of the n by n matrix ring, I can express B as the sum over I and j. And the sums over I and j will be understood to range from 1 to n. All right, so I'm not going to write it 20 times. It's always going from 1 to n. That's the only sum to consider. In fact, I probably could omit the I and j and not really lose anything. But I'll leave it there. Bij, Eij. So this is a nice computational formula to express the matrix as a sum of kind of basic pieces. I'll give you a 2-by-2 example just to make sure we're on the same page, okay? So B would be B11, B12, B21, B22, right? So that's like B11, 1, 0, 0, 0, B12, 0, 1, 0, 0, B21, 0, 0, 1, 0, B22, 0, 0, 0, 1. All right, just to make sure we're on the same page. This is E11, this is E12, this is E21. I think I've had some homework on these things. This is E22, but I forget how much I've assigned you guys. So just to be sure. All right, what else can you tell me about matrix units? Like, what is the calculational core? Here's one of them. If you take Eij, all right, and you multiply it by EKL, what you get is you get Kronecker delta, JK, EIL. Now this Kronecker delta is 0, so this is what? 1 if j is equal to k, it's 0 if j is not equal to k. And so that's how you multiply the matrix units, just like that. All right. These toys should be familiar to you from linear algebra. And let's see how we can play with them here. Now, the lemma is the following. This is lemma 3. And the lemma is really the theorem, more or less. I mean, it's nearly the, I guess it's not the theorem, but it's awful close to it. Anyway, here it is. Every ideal of the matrix ring has the form M, N, A. In other words, it's n by n matrices over A, where A is what? It's some ideal of the ring. So it's saying that the ideals of the matrix ring are nothing more than matrices formed over the ideal of the ring itself. Who could hope for anything better than this? I mean, it's a wonderful result. Then the construction is a little bit mystifying, but I'll go through it with you. Because I was very annoyed with myself for not recognizing the proof when I saw it the first time. Anyway, so we'll let script A be an ideal of the matrix ring. All right? And then what we're going to do is we're going to construct our candidate unscript A equal to what? It's going to be equal to A in the ring. I'm going to use X because there's too many A's here. So X in the ring such that X times E11 is an element of script A. All right. So this E11, I can use kind of dot dot notation. It's 1, 0, 0, 0, dot 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 0, dot 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 0, dot 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 0. Okay, it's that thing. That's always there to play with. That's why we're going to use that for the proof, is whether n is 1 or 2 or 2000, that's always in there to mess with. All right? Now, his initial claim is that this is an ideal. Let's prove that this is an ideal. Well, let me not write that. Let me just say, well, how do we show something's an ideal? We should do what? Let x and y be an A, right? We'd like to show that they're difference. And let's let R be in the ring, right? I'll write in a different color what we want. What do we want? We need that x minus y, Rx, and XR are elements of A again, right? If we have those three things, it's an ideal, right? Okay, so what happens here? If we look at x minus y times E11, what do we get? And what happens when we look at Rx times E11? What happens when we look at XR times E11? The first one's the easiest, right? Because this just gives us x times E11 minus y times E11, which we're looking at the difference of things in the ideal script A. But script A is an ideal, so it's closed under differences. So this is an element of script A. Therefore, x minus y is an element of A. How about the next one?
R times x.
Right, exactly. This is R times xe11, which is to say that it's R times something in where? Something in script A, but script A is an ideal. Therefore, this is also an element of A, which shows me that Rx is an element of Latin A.
Although, don't we have to have something in the matrix ring times something in script A, rather than something in the ring times something in script A? So we have R times A something.
Fair enough. So Sam has spotted a slight hole in my proof. So x times E11, I should have written as xi times E11. So now this is the n by n matrix. So this would actually be the matrix x, 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 if you like. It's x times the identity matrix. That's in the ring, right? Well, I'm still not getting the point. I mean, all right, fair enough. And I would like to see that detail here also. You got me. Well, that's what this means also, right? Well, anyway. Let me just say that. I don't think I need it on the other factor. I just need it on the first one, so that I actually have a matrix, right? This is something in A, but A is an ideal, so its product is in there. All right. And likewise, right, XR E11 is equal to, I've lost my place here.
Because R is a multiple of the identity, so it should commute with any matrix.
Yeah, I'm sorry. I just had a moment of consternation here. Yeah, so that is, like you guys just said, I can commute. Curses. You guys have gotten me. You guys have gotten me off my pace. Where was I? So XR So this is equal to, excuse me, x E11 times r, right? The point is that r commutes with E11. That was what you were telling me a second ago, right? And then this is nothing more than x E11 times r times the identity, just the same, which again is an element of A because A is an ideal. So we're looking at a product of a matrix which is an A with a matrix which is anywhere. It doesn't matter where. Script A is an ideal. Okay, so there we go. So that gives us that XR is an element of A.
Sorry, where's the identity matrix come from?
R is a ring, so it's got an identity. So you can put ones on the diagonal, and that gives you the identity matrix.
I'm saying R is in big R or R is in N R?
I said right here that X and Y are in A and little r is in R. It's that R that I'm talking about.
So you're saying I is just whatever identity maybe?
I is IN. It's the matrix. It's the diagonal matrix with ones down the diagonal, just like usual. I is the usual identity matrix from linear.
Yeah, I'm just not exactly sure why I has to be.
Because otherwise, I don't have a matrix. I mean, I'm given that A is an ideal in the matrix ring. That tells me that closure left or right multiplication by a matrix is closed back in the ideal again. Now, the scalar R naturally corresponds to a matrix, R times I, but the scalar R is itself technically not a matrix, which is why Sam's comment was helpful. Yeah. Okay, so what does it remain to do? So we still need to do what? Now we need to actually show, I mean, we've got this ideal, right? You're like, well, that's great, it's an ideal. Now we need to show that that is in fact the case, all right? So how do we show that this well, there's nothing to show, that's dumb. You need to show that this is actually equal to my script A, okay? That's what we want to do. So suppose B is an element of the n by n matrices over our ideal A, right? Then B is the sum over I and j of Bij, Eij, where what? Where Bij are in the ideal A. And if you look at that, then you might notice that Bij, Eij, all right, is equal to, and here's a sneaky step, Ei1 Bij, well, I'm sorry, let me put another sneaky step in here. Let me put a slightly less sneaky step here. So Bij, and I'm going to rewrite Eij as Ei1 E1j. All right? And then I'm going to make another sneaky step, which is to rewrite I'm leaving Ei1 alone. I'm going to take the E1j and I'm going to rewrite it as E11 E1j. My choice of I here is suboptimal. So all I'm doing is I'm exploiting the fundamental multiplication identity, right? Like if you put j equals to k, right? This will give us, for example, if we put j equals to k equals to 1, this gives us ei1 e1l equal to eil, among other things. So I'm just exploiting that identity over here to create an E11. And why would I do that? Well, because then, remember the Bij's commute with everything here. So I can move the EIL out front. I can put my Bij E11 in here, right? And then I can put my E1J over there. What's that give me?
Bij E11 is an element of A.
Right.
Then that's also an ideal by what we just showed, so that will things in A.
Right.
Which makes B a sum of things in A also in A.
So this is an element of A. This is, these and these are matrices. Because, so this is an element of A again. Because script A is given to be an ideal. Right? So what does that show? That shows that every piece of B is in script A. So this implies that B is an element of script A, which implies that the n by n matrices over A is a subset of A. What's that?
Instead of EIL, should that be EI1?
Yes, thank you. Right? Now we got to go the other way. How do you prove that A is a subset of that? Right? If we have B is an element of script A, I want to show that in fact that's a matrix with coefficients from my ideal, with coefficients from my ideal A. And so the way to do that is, I want to show let's say B PQ is an element of A for all PQ. So we'll write B is equal to the sum. You can write B is equal to the sum over P and Q of BPQ, EPQ. So to show that B is a matrix over A, it suffices to show that an arbitrary coefficient of the matrix is an A, right? And here's the thing that I was upset with myself for not recognizing. He's got it worked out, but I'm just going to get straight to the point here. If I take E1P times B, right, times EQ1, what does that give me? Right, if you work it out, this gives us B, PQ, E11. I could work it out. Maybe it's good for me to do that. What did I have? E1P, B, EQ1. All right, so this gives me E1P. I'm going to use some other letters for the sum this time. I and J again. B, I, J, E, I, J. I take that. I multiply over here by EQ1. Right? And then all I have to do is just use properties of matrix multiplication and sums and so forth. So this is going to be sum over ij, and I can pull the bij out front to get it out of the way. And then what I've got is I've got E1p, Eij, EQ1. So this one gives me a Kronecker delta JQ EI1. Now that Kronecker delta kills off. This will kill the sum over j and leave me with j equals to q. And it just leaves the sum over I. So I've got b, I, j is now q, e, 1p, e, I1, right? Then this gives me Kronecker delta pi E11, which kills this sum off and gives me a B PQ E11 as I claimed. The standard linear algebra calculation, really. But what does it show? Right. So this is an element of A. Right. Thus, BPQ is an element of the non-script A, which is all I needed to prove that everything in the ideal is in fact built from a matrix over this ideal A. All right, so anyway, it's a rather interesting result, I think. And really, this construction right here is kind of surprising. But I don't have a good intuition for why we're doing this yet. I mean, it worked out really nice, but why are we doing that? I don't have a good answer for that just yet. Now, the real reason this is interesting, of course, is the theorem that you get from this. What theorem do we get from this? Right. So R is R a ring, all right? Then M, N, R is simple if and only if R is simple. So the proof is very simple with the lemma in hand, right? Think about it. If M, N, R is simple, what does that mean? These are the only ideals, right? Of the matrix ring. If A is ideal of R, then what? Mn A is ideal by lemma, right? Hence, the ideal MNA is either equal to what? 0 or what? The whole thing. But then what? If the set of matrices over an ideal is just the 0 matrix, the ring getting just the 0 matrix, this clearly implies that A is equal to 0, right? As in a subset of the ring. This is the 0 matrix. That's an n by n. And on the other hand, if this is, if you have MNR is equal to MNA, what's that say? This implies that R is equal to A, right? Could you show that? How would you show that carefully? I claim it's intuitively obvious. How would you prove it?
We could use the same sort of E11 mapping back and forth as we did on the
I don't think you need to, because you could just take an arbitrary element in there, claim that it's formed by a sum of those units times coefficients, and then I don't know. It might not be as easy as it is.
I think it's intuitively clear, but I'd actually have to think about it for a minute to actually prove it. Yeah. certainly a contradiction would be an easy way out. The other direction here, if R is simple, well, the other direction's clear. I mean, if R is simple, then what? If R is simple, then only 0 and itself are ideals of it, right? Consequently, the only ideals of this, by the lemma, are the 0 matrix ring or the whole matrix ring. Okay. And a corollary to this theorem, so I'll just say the converse direction is similar. Corollary to this is that if R is a division ring, all right, if R is a division ring, then M and R is simple. Remember, what do we have about division rings? They're simple, right? So since division rings are simple, theorem that says that the matrices built over a division ring is simple. And then this gives you an interesting example. He says if you look at the 2 by 2 matrices built over Z2, this is a simple ring. Which is what? It's a simple ring which is not a division ring. Because there are elements in M2, Z2 which are not invertible and yet are non-zero. So this is a simple ring which is not a division ring. It's, in fact, he claims it's the smallest such example. Although I did not see the proof of that. But maybe it's obvious, I don't know. Now, interesting thing for me is if you go on, eventually, chapter 11, we find out a theorem which has a name. And one part of that theorem, this Wedderburn theorem, says the following. If you have R is semi-simple, all right, and we'll have to wait till Math 422 to talk about what that means, but if R is semi-simple, then in fact you can write R as isomorphic to the direct product of matrix rings over division rings. And on the other hand, if you have a commutative ring, right, when R is commutative, then R semi-simple means what? What are the division rings? What's that?
You have theorem about R is simple and R is commutative.
R is commutative. Semi-simple doesn't mean simple. It means semi-simple means that you can write it as the direct product of simple rings. So in that case, in that context, this is not actually surprising, but there are actually other conditions on the the Wedderburn theorem, which are more sort of interesting. Anyway, I'm just saying we'll come back to this discussion in chapter 11. I'll leave it at that for here. Okay, so section 3.4 then, finally, talks about ring homomorphisms, okay? And there's one example in this section I absolutely must do today to try to give you a sense of how important the first isomorphism theorem is. All right? And so the first isomorphism theorem, what does it say? I'll write it down for you. Theorem 4 in section 3.4 it states the following. It says if you've got theta going from R to S, right, a ring homomorphism, it's kind of funny, we've already talked about ring isomorphisms a fair amount earlier, right? But now he's getting back to ring homomorphisms. Yeah. Then you can define theta bar from R mod the kernel, which is, by the way, an ideal, to the image. All right. Given by, so here's what you do, theta bar of x plus the kernel. Guess what? You map that to theta of x. All right? Is an isomorphism. So, you know, that's the first isomorphism theorem for rings. And I'm saying it's a ring isomorphism, obviously. Check this out. So this is example 11. In example 11, it asks us to show that if A is an ideal, of R, all right, then Mn of A is ideal of MnR, all right? And so what you do, right, is we need to define a mapping, let's say phi, which goes from what? From the n by n matrices over the ring to n by n matrices over R factor, R mod A. Can you guys tell me what the map should be? Let me start you out. Phi of the sum, I and j, of Bij, Eij, equals to what? Maybe I need some notation. Let's let pi that goes from R to R mod A be quotient coset mapped, right? So like pi of x is what? X plus A. All right? So with that notation, how would you define phi? Yeah, exactly that. Sum over, so all you do is just map the coefficients to their corresponding cosets. It's exactly that. And you leave that Eij out there well enough alone. This is now an element of the n by n matrices over the quotient, right? And you can work it out. That is, in fact, a ring homomorphism. A little bit of calculation. It's easy to do in view of the notation that I introduced for the lemma. It's very straightforward to use that notation to prove it, right? And what's its kernel?
Matrices over A.
Exactly. It's the matrices over A. And so, n by n matrices over the ring, quotient by n by n matrices over an ideal, is isomorphic to n by n matrices over R mod A. That is the power of the first isomorphism theorem. That would be like, think about working that out without the first isomorphism theorem. This is very nice. It's very nice. I know you don't believe me yet, but it's true. It's like, it'd be nicer if you didn't test on it. Yeah, I know, I know. Anyway, let me give you back your test. You can shut it off.